Welcome to clickmyproject.com. Reduced complexity, robust MIMO decoders. We consider the effects of channel estimation errors on the symbol error rate performance of MIMO systems. The following are our main contributions. Using a correlated multivariate Gaussian channel estimation error model, we derive the optimal decoding metric, which is the maximum likely decode metric, by utilizing the known second order statistics of the errors. This is important because in practice, channel estimation errors are correlated due to the channel correlation as well as estimation methods, which induce correlation in the errors. Using the optimum decoding metric for detection requires an exhaustive search through all possible transmitted signal vectors, and this is not implementable in practical settings. To overcome this problem, we propose an alternative decoding metric which approximates the optimum rule. This approximated metric still accounts for error correlation in that the main block diagonals of the error covariance matrix are used. Using the approximated metric, we formulate a tree search algorithm that has substantially lower complexity than the brute force search of ML detection. We term the algorithm as the brute force robust sphere decoder. We derive analytical upper bounds on the pairwise code word error rate and symbol error rate performance of the optimum ML metric as well as the robust sphere decoder. This is the flow of our project. It consists of 5 modules: MIMO system model, optimal decoding metric, approximate decoding metric, robust sphere decoder, and performance solution. In MIMO system model, we consider the received signal of the MIMO. The model for generic multiple input multiple output system can be written as y equal to hx plus n, where x denotes the complex transmitted signal vector of dimension n cross 1, and x is drawn from a set of x infinite cardinality. Y denotes the noisy received signal vector of the dimension p cross 1. H is the channel matrix of the dimension p cross n with independent elements h representing the uncorrelated Rayleigh fading, and t and n small n represents the vector of independent complex Gaussian noise with n. After that, optimal decoding calculation. Using a correlated multivariate Gaussian channel estimation error model, we derive the optimum decoding metric, which is the maximum likelihood metric, by utilizing the known second order statistics of the errors. This is important because in practice, channel estimation errors are correlated due to the channel correlation as well as estimation methods which induce correlation in the errors. The next is approximate decoding metric. Using the optimum decoding metric for detection requires an exhaustive search through all possible transmitted signal vectors, and this is not implementable in a practical setting. To overcome this problem, we propose an alternative decoding metric which approximates the optimum rule. This approximated metric still accounts for error correlation in that the main block diagonals of the error covariance matrix are used. After that, the robust sphere decoder. To reduce the complexity of the decoding while maintaining the reasonable accuracy, we propose an approximate metric and a reduced complexity search algorithm for it. Using the approximated metric, we formulate a tree search algorithm that has a substantially lower complexity than the brute force search of ML detection. We term the algorithm as the robust sphere decoder. In performance evaluation, we derive the analytical upper bounds on the pairwise code word error rate and symbol error rate performance of the optimum ML metric as well as the robust sphere decoder. The computational complexity of the brute force search is severely limited by the number of searches required. Simulation results show that our proposed decoder has less symbol error rate and computational complexity. Open the source code folder, run main.m file. Figure 1 shows the modulated scattering plot of the QA modulation of the input signal vector, as shown in the figure 1. Figure 2 shows the symbol error probability for 16 QA modulation. This is the theory, and the optimal approximate decoding between symbol error rate are shown here. In figure 3, we display the average number of nodes visited for our proposed method. This is for 4 cross MIMO with 16 QM, and this is 4 cross 4 MIMO for 64 QM, and this is 4 cross 4 MIMO for 256 QM. Node visitor is minimized is in our proposed method. This is the average SNR versus computational savings ratio of our proposed algorithm. This is for 6x6 MIMO with 64 QAM, and it is for 4x4 MIMO with 256 QAM, and it is for 4x MIMO with 264 QAM. Here I compared the existing and proposed algorithm of symbol error rate. This is the 16 QAM, and it is our proposed method has a less symbol error rate, and also the same of the symbol error rate curve, and this is the 64 QAM symbol error rate, and it is our proposed that is dotted line shows in the proposed method, and this is for 256 QAM output. Compared to existing method, our proposed method has a less number of symbol error rate, and this figure 6 shows for the computational complexity of a nodal metric function add multiplication, and the equation present in our base paper add multiplication. Compared to existing method, our proposed method has less computational complexity and less symbol error rate. Thank you.